Okay, let's get into Chapter 4, which is going to cover reactions in aqueous solution. This is probably going to be the longest and most complex chapter out of the 10 that we're going to be covering this semester. So, in your book, they start off Chapter 4 with the concept of molarity, and that's something that I covered at the end of Chapter 3. So, you will find homework problems and so on related to Chapter 4 that have to do with molarity. So if you want information on that, just see the video I made for Chapter 3. For now, we're going to jump into the next concept that's covered in Chapter 4, which is the notion of electrolytes and non-electrolytes. So in aqueous solutions, which is a solution where water is the solvent or the main component of the mixture, electrolytes are substances that dissolve in water and split apart to produce conducting solutions of ions, and by conducting I mean electrically conducting. Now, these are mostly ionic compounds. We'll see kind of a more comprehensive list of electrolytes in a later slide. But a good example of a substance that's an electrolyte in water would be sodium chloride. So sodium chloride, of course, as you know from the previous couple of chapters, is a substance that is made up of sodium plus 1 cations and chloride minus 1 anions. As a pure substance, it's solid, but as you probably know from your own life experience, sodium chloride pretty easily dissolves in water. And when it does this, it dissociates, is the term, into sodium ions and chloride ions that are separate and surrounded by water molecules. So it dissociates into these positive and negative ions that it's made up of that are floating around separately from each other in the aqueous solution. In just pure sodium chloride, those cations and anions are packed together, like the diagram that you saw in Chapter 2. But in an aqueous solution, they're going to be floating around surrounded by water molecules and separate from each other. Now, contrast this to non-electrolytes, which are substances that don't produce ions when they dissolve in an aqueous solution. So there's a couple of reasons something could be a non-electrolyte. The first and most fundamental reason would be if it's not even dissolved in the first place. And the second reason is that some compounds can dissolve in water, but when they do that, they don't produce ions. A good example of this, and one that, like salt, also comes from the kitchen, is sucrose, which is C12H22O11. This is a covalent compound, so when it dissolves in water, you have sucrose molecules floating around dissolved in the solution, but there's no ions there. There's just covalent bonds between carbon, hydrogen, and oxygen atoms. So when sucrose dissolves, it splits apart into separate molecules, but the atoms that are part of each molecule don't split apart from each other, and there's no ions produced in the solution. One of the easiest ways to tell if a solution contains dissociated ions or not is to test whether it's electrically conductive. Now, the first thing you need to know to understand this test, and something that is maybe a little bit counterintuitive, is the fact that on its own, water is actually electrically insulating. Now, that might seem a little bit strange when you think about the fact that one of the things they warn you about when you're a kid is that if you see a thunderstorm coming, for instance, you're supposed to get out of the pool because if lightning strikes the pool, you could get electrocuted. Now, why do they tell you that if water is not an electrical conductor? And the reason is any sort of water that you'd be swimming in normally is not pure water. It contains dissolved ions. So, for instance, pools are chlorinated, so they contain lots of chloride and other chlorine-based ions. Those ions cause the pool water to be electrically conductive. And also, if you go swimming in, for instance, the ocean, that contains a lot of dissolved salts, since ocean water is salt water, so it's going to be electrically conductive as well. Both of those things contain ions that are electrically conductive. But pure water with no dissolved ions, so like distilled water or something, is actually a good electrical insulator. Now, if you have dissociated ions present in solution, then if you take a conductivity apparatus, like the one that you see in the pictures at the top of this slide, the dissociated ions in the aqueous solution allow electric current to flow between two electrodes placed into the solution. And so if you hook this up to a power supply, you'll have a complete circuit, and if you have a light bulb as part of that circuit, then the closed circuit will allow electricity to flow through the light bulb and turn the light bulb on. If, on the other hand, you have an insulating solution, so one with no ions dissolved in it, when you hook this up to the power supply, the circuit's going to stay open because there's no way for electricity to flow between those two electrodes in the solution. And so your conductivity apparatus will not allow electricity to flow through a light bulb, and the light bulb will stay off if you perform this test with a non-electrolyte solution. Now, a distinction needs to be made between different types of electrolytes, and specifically, besides the fact that some substances are electrolytes and some are not, the substances that are electrolytes can be further broken down into strong versus weak electrolytes. And strong electrolytes are compounds that dissociate to a large extent when they're dissolved in water. So effectively, we can treat this as 100% dissociation. And compounds like sodium chloride or potassium chloride, which is analogous, it just has potassium cations instead of sodium cations, are good examples of strong electrolytes. They completely dissociate in water into cations and anions. Some substances are also weak electrolytes instead of strong electrolytes, and that means that they only dissociate into ions to a very small extent when dissolved in water. A lot of good examples of weak electrolytes are substances that are so-called weak acids, which we'll get into more in a little bit. And any weak electrolyte is a substance that's composed of ions that only dissociate to a small extent. So a good example of this would be acetic acid, which consists of hydrogen cations and acetate anions. And we can see these double arrows, so unlike a normal reaction arrow which just points to the right, we have arrows pointing in both directions here, and this is to show that in water, acetic acid splits apart into these ions only to a small extent. Acetic acid is actually the solute in vinegar, so in the concentrations that acetic acid is found in vinegar, usually this dissociation only takes place to about a 5% degree. So for instance, about 95% of the acetic acid will be present as covalent acetic acid molecules, whereas the remaining 5% of it will be present as dissociated H+ cations and acetate anions. Okay, so more about acids and categories of electrolytes in general here. So this table does a decent but not comprehensive job of showing you examples of different categories of electrolytes. So under strong electrolytes, we have strong acids, and I'll show you a list of those later. These are acids that dissociate completely in water. So just like sodium chloride dissociates completely into sodium ions and chloride ions, a strong acid, like say hydrochloric acid, HCl, will dissociate completely into H+ and Cl- ions in solution. And there are other strong acids as well. Other compounds that are strong electrolytes are ionic compounds, but only certain ionic compounds. So specifically, only ionic compounds that are soluble in water are going to be strong electrolytes. And by soluble, I mean capable of dissolving. So, for instance, we looked at sodium chloride earlier. That's a soluble compound because that can dissolve in water to a very large extent. Not all ionic compounds, though, are capable of dissolving, and that's actually something we're going to cover in a lot of detail in a later section. Under weak electrolytes, we have really just two types of compounds. The first type is weak acids, and the second type is weak bases. And how you determine, for instance, if something is a weak acid or a weak base is, again, something that we'll cover in more detail in a little bit. And finally, we have non-electrolytes. So non-electrolytes include all covalent compounds, essentially, so all molecular compounds. And they also include any compounds like ionic compounds that might otherwise be electrolytes but are incapable of dissolving. So insoluble ionic compounds would be non-electrolytes. Okay, let's look at strong and weak acids and bases and how you can recognize them and what you need to know about them. So in the first category here, we have strong acids, and these are all going to be strong electrolytes. The strong or weak in acids and bases essentially refers to whether they are strong or weak electrolytes in both cases. As far as we're concerned, there are only 6 strong acids, and those are the acids listed here. So we have nitric acid, perchloric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. Now, it's worth pointing out that we have 3 acids based on polyatomic ions, nitrate, perchlorate, and sulfate for nitric, perchloric, and sulfuric acids respectively. And we also have 3 binary acids in this list. And the binary acids are all based on halogens, so hydrochloric, hydrobromic, and hydroiodic acids based on chloride, bromide, and iodide ions. Because of this trend for these last 3, it's a really common error to assume that HF, hydrofluoric acid, is also a strong acid. In fact, it's actually a weak acid. So that is something you'll need to keep in mind when you are going through this list. Now, how do you determine if something is a weak acid? If you know your strong acids, it's pretty easy. So a weak acid is any acid, so some compound formula that has H plus cations plus some sort of anion, but it's not on the list of strong acids. So if you have something that meets this criteria where you've got H plus combined with some other anion, then it's either going to be one of these strong acids, or if it's not one of those 6 explicitly, then you can assume that it's a weak acid. So for instance, acetic acid, which is H plus and acetate ions, would be a weak acid, probably the most common example of a weak acid, but any other anion you can think of, whether monoatomic or polyatomic, that isn't accounted for in the strong acids, would count as a weak acid when combined with H plus. Alright, let's move on to strong bases next. So hydroxide is OH minus ions, as you can see over here. Any alkali metal ion combined with hydroxide anion will give you a strong base. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, or cesium hydroxide, these are all strong bases. And again, I would encourage you to look at the periodic table if you're not sure where those elements are coming from. All of those are the alkali metals, so the elements in group 1 that all form +1 cations, with the exception of hydrogen. Besides these 3, there's also 3 of the alkaline earth metals form strong bases with the hydroxide anion. Now, not all alkaline earth metals do this, and keep in mind that alkaline earth metals all form cations with a +2 charge, so the correct formula for these are going to have 1 metal ion to 2 hydroxides. So we have calcium hydroxide, strontium hydroxide, and barium hydroxide. If we ignore radioactive elements, these are the 3 alkaline earth metals that are at the bottom of group 2. Now, what constitutes a weak base? So, just like a weak acid is H plus any anion that's not in the strong acid list here, you can assume that any ionic compound that has hydroxide anions and isn't in the strong base list is going to be a weak base. And as we'll see later, any compound that has hydroxide anions that isn't one of these over here is going to be insoluble or capable of dissolving in water, which prevents it from being a strong base. There's also one other weak base that's very common that you should know about, and that is this compound here, ammonia, NH3. Now, that doesn't have any hydroxide ions in it, so how exactly that will behave as a base will become apparent later on when we get into details on acid-base reactions. And to kind of summarize this last chart, we can say that hydroxide compounds, if they are soluble, are going to be strong bases, and if they're insoluble, they can be weak bases. And then also we have ammonia down here, which is not one of those two things, but it's a really common weak base.